So we looked at our bimolecular reactions, so SN2 and E2, and compared their um, various aspects of them, the mechanisms, the effect of solvent and nucleophile and base and all of that. So we're going to turn our attention now to at the unimolecular reactions, and that's SN1 and E1. So let's just take a look at this reaction. So we're going to take this alkyl halide and react it with ethanol. Just a side note, I've referred to this before, but just so we're all on the same page, ET is just our shorthand for an ethyl group. And so ETOH is just this alcohol, ethanol. And when we react this together, we'll get a mixture of two products. We'll get this, where a substitution has occurred, and then we'll get the elimination product as well. Now, if I were to ask you, do you think that the substitution product is formed through an SN2? Hopefully, you would say, no, SN2 is not possible since the leaving group is on a tertiary carbon. It's too sterically hindered for SN2 to occur. And they say, well, how was the elimination product formed? Could it be E2? Well, E2 isn't possible since E2 requires a strong base. So in this case, E2 is not favored since a strong base isn't used. Okay, but we know this reaction still happens. We know that we get this mixture of products. So the reaction has to proceed through different mechanisms, not SN2 and not E2. So the mechanism must be stepwise then, where SN2 and E2 were both concerted mechanisms. They happened all at once. Whatever mechanism that this reaction on the page is going through cannot be concerted. It has to be stepwise. And so for both the substitution and elimination here, the first step of the mechanism involves forming a carbocation. Now, for both substitution and elimination here, that formation of the carbocation is the rate determining step. That's the step that requires the most amount of energy because we're going from a carbon that has a full octet, and when that leaving group leaves with its electrons, you get a carbon with only 6 valence electrons around it. That's not stable, it's not happy. So that requires a lot of energy to accomplish that. And then if it reacts with the nucleophile, we get the substitution product. If it reacts with a base, we get the elimination product. Now I'll go in depth into the mechanisms for each of these, in which this would be SN1 and this would be E1. On the following pages, I'll go through the mechanisms. So let's start off by looking at SN1. Now, again, just to review, that S stands for substitution, the N stands for nucleophilic, and the 1 stands for the fact that it's unimolecular, meaning there's only one chemical species involved in the rate determining step. So in the reaction on the previous page, let's go through the mechanism. We're going to assume it's going to go through SN1. We won't worry about E1 right now. So the first thing that happens is the leaving group leaves. Notice in this step, the nucleophile is not involved at all. So the rate determining step is the formation of that carbocation. And I want to highlight something important here, that that carbocation is stabilized by polar protic solvents. Not only is the carbocation stabilized, but the leaving group is stabilized as well. Okay, so one thing to make a big note of, SN1 is favored by protic solvents. That was a big difference than SN2. SN2, recall, is favored by aprotic solvents. So now, in the next step, we'll have our nucleophile come in. So our nucleophile here was methanol. Me is our shorthand for methyl. Now, again, I want you to highlight something really important here. Notice that nucleophilic atom does not have a full negative charge. It's partially negative. So I want you to think in your mind, what do you think about that as in terms of a quality of a nucleophile? Do you think that's a good nucleophile or a poor nucleophile? Okay, so think about that. I'll come back to that question in a little bit. So the oxygen uses a lone pair to make a bond to the carbocation. And we have this intermediate. Now, this is not our final product. Oxygen doesn't like to have that positive charge. So we're going to have one more step here. And we'll use some more methanol to do a proton transfer. And this is our final product. Now, I want you to take a look at all of these steps. And I want you to recall back in the previous unit some of the common mechanistic steps. Notice that we have like three of them here. The first step is leaving group leaving. That's a common mechanistic step. Second step is nucleophile attacks an electrophile. And then the third step is a proton transfer. So all three of these are not like brand new types of steps. They were in the previous unit. Now, one thing I want to highlight is that a lot of SN1 reactions are known as solvolysis reactions. And this is where the solvent is also the nucleophile. So that goes back to the previous point I made that this SN1 stabilized by protic solvents. So methanol is both a protic solvent and it's also the nucleophile in here. And then finally, just a word about the kinetics. And I mentioned this earlier, but I'll highlight it again. The rate is dependent upon the concentration of the substrate only, not the nucleophile. Because again, look at the rate determining step. The rate determining step involves the leaving group leaving. It does not involve the nucleophile at all. Now, let's compare this to E1. So again, to review, oops, E stands for elimination, and the 1, like SN1, stands for unimolecular. So the mechanism for E1 starts off just like SN1, the leaving group leaving. Again, that is the rate determining step. So leaving group leaves and you get a carbocation. But instead of the nucleophile acting like a nucleophile, it's going to act as a base and pull off a beta hydrogen. Notice that how similar that is to E2. In E2, a beta hydrogen was always pulled off. It's the same thing here. I'm just doing it stepwise instead of all in one step. So a beta hydrogen is pulled off, and then the electrons from this carbon-hydrogen bond move down to form a pi bond. So just to emphasize again, it's the same first step as SN1. Now, in general, so I don't want to say that this is, a scientific fact 100% of the time, but in general, SN1 is favored, meaning you'll usually get a lot more SN1 product than you will E1 product. Doesn't mean E1 never happens, it just means you have a lot less of it. So SN1 is generally favored. The substitution will be the major product, except when a tri or tetra substituted alkene can be formed through E1. So if we look at this energy diagram here, the energy of the rate determining step is the same. So the activation energy is the same for E1 and SN1. So what's the difference then? The difference happens after the carbocation is formed. Generally, the SN1 product is more stable, and the E1 product is less stable. Now, what would make that different is if you had, say, a tetra substituted alkene that could be formed. So, as I said, SN1 is generally favored. It's the major product, except if you can make a very stable alkene, like a tri or tetra substituted alkene. Now, one thing I do want to point out is that both of these mechanisms involve carbocation intermediates. So you always need to keep that in the back of your mind. Since carbocations are formed, you need to be attentive to possible rearrangements. If a more stable carbocation can be formed by rearranging, then it's going to do that. So let's look at an example here. If we do this reaction in water, we get a mixture of substitution products. We get some where the nucleophile replaces the bromine on the carbon that it comes from. And then we get some product where the OH is on a different carbon. And then we do get some elimination products. I'm not going to go into those. We're just focusing on how do we get these two substitution products. So let's draw a plausible mechanism that can describe how both of those are made. So since this is going to go through an SN1, leaving group's going to leave first. And we get this carbocation. Now, if I have water attack this carbocation before it rearranges, then I get this initially, and then we'll deprotonate it to form this product. Now, how can I explain through a mechanism how the second substitution product gets made? Because this OH is on a carbon that didn't have the bromine to begin with. So let's start here. I'm going to go back to this intermediate. I'm going to draw that hydrogen there in blue. I want you to focus in on it. How do I get the OH on that carbon? Well, I'm going to do a carbocation rearrangement. So now the hydrogen's over here, and the carbocation is now on a tertiary carbon. So now we can have water attack this new, more stable carbocation, and let's finish off the mechanism. So we'll just do a proton transfer here to get that oxygen to be neutral, and that's how we get the second product. Now, I want to show kind of a really interesting, kind of cool case here. If we do this reaction in the lab, we might predict the products to be this, where we get a substitution product on the carbon that had the leaving group and then a rearranged product. That's what we would predict. But here's the kind of the cool thing. This product is not even observed, not even a little bit. The only substitution product is the rearranged one. And what I want you to do is I want you to pause the video and I want you to think about why we don't observe the alcohol on that primary carbon where the leaving group was. Okay, so now you've had a chance to think about that. Hopefully you took some time. Let's think about why we don't observe that product. So in order, if that product was to happen, we would have to get rid of the bromine on that primary carbon. So hopefully right now you're yelling at your computer screen and saying, no, 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 that's not possible. You cannot form a primary carbocation unless it's resonance stabilized. It's not like, well, I can do a rearrangement. You have to, in order to do a rearrangement, you have to form the carbocation in the first place, and that primary carbocation will never get formed. So that's why we don't observe the nucleophile attacking that primary carbon. Now you might say, well, if I can't form the carbocation, how do I get the rearranged product? Because don't I need a carbocation to do a rearrangement? So let's see if we can describe or come up with a mechanism that describes how that is even possible. So instead of the leaving group leaving, what we're going to do is demonstrate how that leaving group can leave and the rearrangement happens to form a stable carbocation. So we're going to move this methyl first and kick off the leaving group at the same time. And so when that happens, I've done the rearrangement and made a stable carbocation all at once. And then I have the water attack. And then I do a deprotonation. So now I'm kind of back on the template for that SN1. And that's how I get that substitution product. And it also describes why that's the only one that is formed.